Okay, so let's look at where are we looking at? We are looking at 16I, and that's the points of inflection. So let's see. Oh, sorry, wrong pen. Okay, aim. This is 16I, and this is points of inflection. Inflection. The question is, what's going on? What is the point of inflection? Well, we spoke about that. We're dealing with the second derivative here. And in the last lesson, we looked at what happens when the first derivative was zero. The question is, what's going on when the second derivative is zero? So, basically what happens is the curve changes concavity. So when the second derivative is equal to zero, in general, there's always exceptions in math, but in this class, when the second derivative is zero, the idea is that the curve changes. It looks something. I mean, we know it looks something like this. So the idea is this is the point where the concavity changes. So the curve, this is concave down. At the inflection point, the curve now changes to concave up, right? Concave down, concave up. And that's basically it. The other, so once again, we can see, so let me change the color of, no. Let's change, I need some surfboards. So that once again, we see the surfboard is above the curve, above the curve, above the curve. Suddenly, it's kind of like neither at the inflection point, it's neither above or below. Now it's below the curve, below the curve, below the curve. So, yeah, so above and below. Now, and also, or it could change from below to above. That's the idea of the inflection point. So, but I want to get a closer look. So let's go to Desmos and see what's going on. What's exactly happening? So I'm going to go to Desmos.com calculator, and in the upper left-hand corner, we can see that triple dash. And if we scroll all the way down, calculus tangent line, because once again, I'm interested in what's going on with the tangent line. So we see here from the first day, they gave us an example of a sine wave. The g of x is the derivative of the fs. So that's going to be the slope of the tangent line. They give us a slider, a, which is like the x values. So we can see as we move from negative 10 to positive 10, that's where the tangent line moves along the sine wave. And then they create the tangent line using a points law formula, and then they look at the point. First of all, so if we go to the book, they have this interesting example right here. The example right here is y equals x cubed minus 3x squared plus 5x minus 1. I'm going to put that in. I'm going to switch this first example and put that in there. So let's see, we have x cubed minus 3x squared. We have plus 5x minus 1. And we can see here that, so the idea is, we have this tangent line, and the question is, what's going on at the inflection point? Well, first of all, can we figure out what the inflection point is? Yeah, let's just go back to our form, our sheet, and let's actually figure it out by hand. So what was it? Let's see, y equals x cubed. Let's see, minus 3x squared plus 5x minus 1. The first derivative is 3x squared minus 6x plus 5. And then we're looking for the inflection point, the second derivative. So we have 6x minus 6. Just on a side note, wait, how can we show that this is what can we say about this function? How do we know this is always positive? Any suggestions? Oh, because the discriminant is 36. Let's see. No, let's think about that. Is this function always increasing? What do you think? 3x squared minus 6x plus 5. B squared minus 4. Oh, yeah, what's going on there? Yes, sorry. The discriminant is 36 minus 4 times 3 times 5, which means this is less than 0. So that means the parabola is above the x-axis, which means it's always positive. So we can see the function is always increasing, but that's not what we're talking about today. I want to know about the. I'm sorry. I want to know about the inflection point. So let's set this equal to 0. We have x equals 1. So something's going on at 1. Something is going on at x equals 1. So I'm going to move. I want to know the slope of the tangent line at all the points. So you know what? Down here, I'm going to have Desmos evaluate g of a. And that, if we notice this number right here, it tells us the slope of the tangent line. So I'm going to start at like -3. I'm going to start up here at -3.1, and I'm going to move towards a equals 1 or x equals 1 because I want to know what's happening. So let's see. The slope right now is 52, a really steep line, right? I'm moving. It's decreasing. It's decreasing. It's decreasing. It's decreasing. It's decreasing. It's decreasing. I'm now at 0, right? I'm down to 5. Let's keep going. It's decreasing, it's decreasing, it's decreasing, it's decreasing. When x or the a equals 1, my slope is 2. But now what's happening as I move the slope? What's happening? It's increasing, it's increasing. That's the idea of the inflection point. So once again, the slope was always remained positive, but it was decreasing. It got to x equals 1, and then it started to increase again. That's the idea behind the inflection point. So to find the inflection point, so let's go back to the notepad. So, and let me change the color. Let's change to black. So once again, to find the inflection point, set the second derivative, or d2y over dx squared, or equal to 0, and solve for x. In most cases, when you set the functions in this class equal, the second derivative equal to 0, the x values are going to be inflection points. The exception, which that might be your exploration to study cases like that. For example, y equals x to the 4th, right? Y equals x to the 4th kind of looks something like a parabola, but it's really flat here. And the idea is that it's always concave up. So at x equals 0, because we know the first derivative equals 4x cubed, set that equal to 0. We know at x equals 0, there's a minimum, right? But the problem is, when we set the second derivative equal to 0, it's also, and then even the third derivative, what do we have? 12. No, forget that. So it's not an inflection point. So that's the idea here. So that's the problem. That's the exception to the rule. Anyway, 16I, work on the problems. Good luck.